In the preceding slides, we discovered that a phase is stable if it has the lowest Gibbs energy. Changes in phase stability arise because the pressure and the temperature affect the Gibbs energy of the substance differently in different phases. So our purpose here is to develop an understanding of the dependence of the Gibbs energy on temperature and pressure, so we can compare quantitatively the magnitude of the Gibbs energy for each phase at any temperature and pressure. To do so, we start with the equation relating the Gibbs energy G, the enthalpy H, and the entropy S, and given as G equals H minus Ts. We then use the definition of the enthalpy H as the sum of U plus PV and obtain G equals U plus PV minus Ts. So the change in Gibbs energy, dG, is equal to the change in the function U plus PV minus Ts, which we can write as du plus d of PV minus d of Ts. Using the first law of thermodynamics, we replace du by dq plus dw and obtain for the change in Gibbs energy dg as dq plus dw plus d of PV minus d of Ts. Since u is a state function, the change in u is independent of the path taken, so we can choose a reversible path to calculate du. We can write dq is equal to TdS from the second law of thermodynamics and replace dw by minus pdv. We also expand d of PV as p times dv plus v times dp and do the same with the change in Ts. So we get dg equals TdS minus pdv plus pdv plus vdp minus TdS minus sdt. This equation can be simplified to yield a very important equation dg equals vdp minus sdt. You should not memorize this equation, but learn how to derive it, as it is an equation that has widespread use in many areas of thermodynamics. Over the next 4 slides, we are going to use this result to shine some light on the variation of G with first pressure and then temperature.